Hello, welcome to the course. Thank you for being here. I hope you're ready to learn. I'm going to try my best to make this as straightforward as possible. This is the nitty-gritty or meat and taters of what we're going to get into, which is the electrical cardiac anatomy or the cardiac conduction system. For more information on this or to further your understanding, I recommend a semester-long cardiology course where you'll learn rhythm interpretations, 12-lead electrocardiograms, and really in-depth pathophysiological stuff. Today, we're going to learn how to trace the lightning. My name is Corey Holland. I've been in EMS for about 8 years now, from an EMT into an advanced EMT and now to a paramedic. Cardiology has been a large area of interest for me throughout my whole career. The heart is the most fascinating organ in the body, and for a plethora of reasons. And I encourage you again to educate yourself on the heart as much as you can. You can get lost in all the intricacies of cardiology. But before we can start looking at any sort of rhythm strip or electrocardiogram or anything of that nature, we got to take a few steps back. While you're looking at all those squigglies and waves and lines, it can get really confusing. Very quickly, too, if you don't really understand what you're looking at. And in order to understand that, we have to start with anatomy. So the heart has 4 chambers, 4 valves, and 5 major blood vessels, immediately connected to it, and things of that nature. We're going to go over those here in just a second. I will forewarn you, I went to school for business management. I did not go to art school. Here we go. So you've typically seen the heart drawn something like that, and that looks great if you're a kid or you work for Hallmark or something, but that's not really the world that we live in. In a roundabout way, the heart kind of looks like a kidney bean. Alright, so we're looking at it sort of just like this, straightforward, assuming that this is the patient. This would be the patient's head, this is the patient's right side, this is the patient's left side. So let me make a clearer note of that here. This is the right side, this is the left side. Okay, so the 4 chambers that we have to work with here are the atria that sit at the top of the heart and the ventricles that sit at the bottom of the heart. And in a roundabout way, we can sort of see those denoted sort of like this. These are the top portions of the heart. This is the bottom portion of the heart. So this is the right atrium. And over here, we have the left atrium. Pretty straightforward stuff. The atria sit on top of the heart, and underneath of those we have the ventricles. The right ventricle and the left ventricle. And the top part of the heart totally comprised of the atrium, the bottom part of the heart totally comprised of the ventricles. We have 1, 2, 3, 4 chambers of the heart accounted for. We have 4 valves here in the heart. The valves are located in positions as such that they prevent backflow of blood into the chamber above it. Backflow of blood is a very bad thing. You can further your education into that in a separate course. But the the four valves that we have start right here in what is the tricuspid valve. And that valve sits right here between, get it a different color here, between the right atrium and the right ventricle. The tricuspid valve, it prevents backflow of blood from the right ventricle back into the right atrium. Blood is supposed to go this way typically. We'll get to that more in a little bit. Backflow is bad. And down here, the bottom of the right ventricle, we have another valve called the pulmonic valve. There's probably a valve to these, eh? Valve. The pulmonic valve prevents backflow of blood into the right ventricle from our first major blood vessel, which is the pulmonic artery, or pulmonary artery, depending on what part of the nation you're from. Pulmonary artery is the first major blood vessel that we're going to talk about. And remember, the difference between an artery and a vein isn't blue blood and isn't red blood. An artery carries blood out of or away from the heart. In this case, blood is leaving the right ventricle into this major blood vessel. The pulmonary artery is leaving through this vessel. That makes this vessel an artery. Very good. The second major blood vessel that we're going to talk about comes over here, sort of in the back, feeds into the left atrium here. Again, forgive my penmanship. Drawing skills have never been a forte of mine. This over here, feeding into the left atrium, is the pulmonary vein. Pulmonary vein. It is the pulmonary vein because blood is leaving from the lungs, the pulmonary area of the body, back to the heart, thus making it a vein. Artery carries blood away, vein brings blood back to the heart. So we have so far 2 valves and 2 major blood vessels accounted for. Wonderful. As blood leaves the left atrium and goes into the left ventricle, we pass through another valve. Keeping up with colors is going to be a challenge for me. And this valve is called, it has 2 names depending on which book you read. It is either known as the mitral valve or the bicuspid valve. So if we were to look at them flat, if we were able to cut some of the valves out and just look at solely the valve, the tricuspid valve is such is that there's 3 little flaps. It opens up, it closes. 1, 2, 3. That's the tricuspid valve. This one, it just has 2 flaps. That makes it a bicuspid valve. Also known as the mitral valve, because everything in science has to have a funny word to it. It is what it is. Wonderful. So we're coming in from the pulmonary vein to the left atrium. Blood leaves the left atrium into the left ventricle through the mitral or bicuspid valve. And then it leaves the left ventricle via our fourth and final valve, known as the aorta. Oh, look at me, colors. I just said that just a couple minutes ago. The aortic valve. And it is called the aortic valve for a very complex and difficult to grasp concept. Blood goes into the aorta after that. And our third major blood vessel here is the aorta. The aorta is the largest artery in the body. Now really, the aorta sort of kind of goes backwards and goes up behind the heart, and that's more of an anatomy and physiology course specifically for the thoracic cavity. Again, we're just focusing on the heart itself. From the left ventricle, blood goes through the aortic valve into the aorta. So we have 4 chambers of the heart covered, 4 valves covered, but only 5 major blood vessels covered. That's a little bit weird. We've got how blood moves out this way, back in over here, out this way. Where does it go? Once the blood leaves the aorta, it completes its whole circuit through the whole body and back, and re-enters the body right over here into the right atrium. Taking a medical terminology class would also benefit you for the next couple of words. Tacos. The right atrium is fed by the, maybe I'll give you some more room here to read my chicken scratch, by the inferior or bottom and superior or top vena cava. Again, this is science, so everything has to have a very complex word for whatever reason. The inferior and superior vena cava are the largest veins, and they bring all the blood from the bottom of the body back up and the top part down. Superior and inferior vena cava feed into the right atrium for the cycle to start all over again. So now we have 1, 2, 3, 4, 5 major blood vessels accounted for. Kapow! Just a quick little review. Into the right atrium via the superior and inferior vena cava, through the tricuspid valve into the right ventricle, through the pulmonic or pulmonary valve into the pulmonary artery, through the pulmonic circuit, back into the left atrium via the pulmonary vein, through the mitral or bicuspid valve into the left ventricle, through the aortic valve, and out into the aorta. That's it. It's pretty straightforward, right? Blood comes in, blood goes out. It's not as complicated as you would think, and it's fairly foolproof. That's what makes the heart kind of cool, because it's foolproof. It's pretty easy. But what makes the blood go through all of these areas? What makes blood go from the left atrium into the left ventricle? A heartbeat, right? When the heart squeezes or contracts, pretty straightforward. Squeeze, open up the valve, blood goes in. Squeeze, open up the valve, blood goes in. Obviously. Well, you would think it's obvious anyway. But what makes the squeeze or the contraction occur? The myocardia, or the muscle cells of the heart, must receive an electrical impulse, or the lightning, telling them to contract or squeeze. Electrical impulses are what make each part of the heart squeeze in their own right. And that is the next thing that we're getting ready to go over. I can keep my notes going here with me here. So the heart is comprised, opportunity for a screenshot now. This will be a little bit different in the classroom. People would just pick up their phones and take a picture of it. But screenshot, because get ready to go away. Only got the one whiteboard. A heartbeat is a funny thing because it's really difficult to see. We know a heart beats because we can put our fingers on pulsatile areas of the body. We can feel it. We put a stethoscope onto someone, we can hear it. But what is a heartbeat? So a quick little roundabout refresher here. We've got this like kidney bean shape of the heart, and in a kind of sort of way we've got, you know, the kind of the outline here that these are the atria. This kind of comes down into the ventricles, right? We got valves and arteries and veins and all that sort of stuff. Refer back to a couple minutes ago to get more information on that. The next thing we're going to talk about is what makes the heart beat. Electricity, lightning. We've already talked about that. The heart has a very intricate network of fibers that send electrical impulses to the myocardium, or the heart tissue, the heart muscle, telling it to contract. There are a few nodes, or large circular groupings of electrical cells and tissue, as well as longer strands and fibers that reach to various parts of the heart that we'll be going over here shortly. So, we started at the top of the heart last time, let's start at the top of the heart again. Sitting atop the right ventricle is the start of the electrical circuit. The top of this pathway is the sinoatrial node, and it kind of looks, I thought this was orange. That kind of looks like I'm drawing with blood here. That's neat. This is the sinoatrial node. You will also hear the sinoatrial node referred to as the SA node, because all these smart people in science come up with really big words and then they say, wow, that's a lot to type and that's a lot to say, so let's just shorthand it. I have our SA node here. This node's at the top of the right atrium, but generates an impulse for both atria. The SA node is what we call or consider to be the pacemaker of the heart. And in an adult, it sets the heart rate generally between, you're probably not going to be able to see that color. Corey, you got to figure this color thing out there, pal. As the pacemaker in an adult, it sets a pulse generally between 60 and 100 beats per minute, or BPM. Alright, SA node, pacemaker in an adult between 60 and 100. In a healthy adult, the SA node acts as the primary or sole pacemaker, meaning the electrical impulse begins here, moves downwards, and it overrides anything down here. It says, hey, we're going to beat at 60 beats a minute. The rest of the heart says, okay, cool. Pretty straightforward, at least if we're talking about a healthy adult. But you may find yourself wondering, well now, hold on a minute. If the SA node sits atop the right atria, but generates an impulse for both, how can it do that if it's only sitting on the right atria? That's a very good question. It's a question that most folks may not know the answer to. You're getting ready to learn it though. There's a small branch of fibers that come off of the SA node. And they kind of do like this. In a roundabout way. At least in Corey's guest bedroom they do. And this small group of fibers that come off of the SA node are called Bachman's bundle. Other one. Bachman's bundle. Little strands that come off of the SA node and they wrap over from the right atrium onto the left atrium, and all that they do is assist the SA node in getting that impulse across to the left atrium. This has no effect on the pace that the SA node sets. It just helps transmit the message, so to speak, that, hey, dude, we're squeezing over here, you gotta squeeze too. He says, okay, and boom, squeeze, happens. It's awesome. Just south of the SA node, we can find the next node, north to south, right? Coming off of the SA node, in this little area here, is our next node. It's probably a little bit more centered, but we're going to roll with this. And this node is called the atrioventricular node. Again, science, big words, we like saying them. First, we're going to shorten that a little bit though, because it's a lot it's a lot to type. The atrioventricular node, or the AV node. Make it bigger to emphasize what I'm getting ready to talk about here. Cool. The AV node follows down the path, and it's awful hard to figure out how it got its name, right? Because it sits directly between the atria and the ventricles. Atrioventricular node it is. Very good. The AV node is next in line to be the pacemaker of the heart should somehow the SA node fail. And if the onus falls onto the AV node will generate a beat or an impulse between 40 and 60 beats per minute. I know, Corey, you could say we were talking about a healthy adult. Yes, we are. But you got to learn the rest of it. So, just for a little bit, this healthy adult's going to be sick. So, the SA node starts out at 60 to 100. For some reason, should the SA node fail, it is the AV node's job to pick up the responsibility as the pacemaker, and it will generate an impulse between 40 and 60 beats per minute. The farther down we go in the heart, the more we'll find. Coming just off of the AV node, we find a thick band of tissue right through here. I think I ruined this marker because I drove through or wrote through some black. Don't you hate when that happens to markers? Cool. This thick band of tissue is called the atrioventricular bundle, or the bundle of His. I'm not writing anything down yet because I may be about to blow your mind. The bundle of His doesn't necessarily have any pacemaker capabilities, but it is a very important piece to this puzzle, to the electrical cycle. Because what the the bundle of His does in this electrical cycle is it sends the cardiac impulse into two directions. So we've kind of got one that goes this way, and then one that will go this way. My girlfriend's going to kill me. These are her markers. But that's okay. I'll write this down using the same color, Corey, because that's what we've been doing. This is the bundle of His. I believe that was the gentleman who discovered it, or the Atrioventricular bundle. Bundle of his is a little bit easier to write about, isn't it? We'll just call it the AV bundle because that's easier to write. They did it, so can we. Sweet. So the bundle of his, no pacemaker capabilities. That's a little bit weird. The other two guys did. The bundle of his is important because it sends this impulse into two directions. I'm like, wait a minute. What's going on there? Well, let's talk about that. So as the electrical pathway leaves the bundle of his, it splits into what will continue to be two avenues for the rest of the heartbeat. All of this is, in theory, one beat, an otherwise healthy adult who at the present is a little bit sick, but whatever. So, as the bundle of his splits into two, we have now the bundle branches that come down. And as you can very clearly see here, with the bundle branches, and we have separated them into the left and right bundle branches. The separation occurs because the fibers split to allow a more focused impulse or more focused lightning on each of the ventricles independently. The walls of the ventricles are thicker and have more muscle mass due to the strength of the contraction that they must use in order to send blood out to their respective areas. The bundle branches are our last pacemaker and only act as such should the SA and AV nodes both fail. If the branches are having to execute their own impulse, these branches fire at a rate of, I had it wrote down, just looked at it, 20 to 40 beats per minute, of course. Per minute here. I'm going to write this part, Corey. Alright, we have our, let's just come right this way. We have our left and right bundle branch. You may have heard, if you've spent time around people in healthcare, you may have heard about bundle branch blocks or bundle branch blocks or bundle branch blocks or bundle branch blocks, because they can be kind of scary. But again, you'll talk about that more in a 12-week course or another more in-depth cardiology course. This is just what the parts of the heart are, what makes a heart beat, and we'll get to something a little bit special later. Alright, so into the ventricles. The ventricles require so much of a specific amount of electricity and all this and that they get their own little pathways. Aren't the ventricles special? But like we were just talking about, the ventricle walls are thick and muscle. Just as doing push-ups and curls would make your biceps bigger over time, the force that it takes to send blood to each of the respective areas makes the ventricles bigger. The muscle mass just increases. And the bundle branches here allow more of a focused impulse to speak to each one separately. Cool, got that. But in order to ensure that the entire ventricle squeezes with the same impulse, there are a few little strands that come off of them and wrap a little bit back upwards here on each side. They sort of do this number, like a Christmas tree. These little strands that come off of the bundle branches are called the Purkinje fibers. Left and right Purkinje fibers. And the Purkinje fiber's job is to wrap back upwards onto the lateral walls of the ventricular myocardium. The lateral walls, meaning closer to the sides rather than the middle. Lateral walls of the ventricular myocardium. These fibers are the end of the road, in a manner of speaking, as they are the end of the cardiac conduction system. The impulse starts here and works its way all the way down. That's it. From top to bottom, we've got the entire heart covered. The SA node acts as the primary pacemaker, followed by the AV node. The pathway is followed through the bundle of his into the left and right bundle branches, and finally these branches reach back up onto the lateral walls of the myocardium into the Purkinje fibers. Every part of the myocardium is covered, every inch of it. This is lightning. This is electricity. Electricity can be cool sometimes, but not when you're hanging a ceiling fan in your living room in the house that you just bought, even though your significant other swears she turns the breaker off and you get lit up trying to install the fan. Not that I'm speaking from experience or anything like that. I love you, honey. Cool. Time for another screenshot here. Take a picture on your phone if you're sitting in the classroom. Ask any questions if you happen to have any. Pretty straightforward. Starts here, zap, and goes down each way. One fluid motion, and this is happening all the time. Electricity lives right here inside of your chest. How cool is that? Everybody ready? I gotta erase some of this stuff to make room for the next part. Actually, I think I know how I'm going to do this. Alright, so we know the parts of the heart, right? And we've also gone over the conduction pathway of the electrical system. Not too complex, but fascinating nonetheless. Now let's flip the script, okay? We know what a heartbeat does. You know, the atrium are here, and then the ventricles are here, and then the valves and the blood vessels, okay, and then the top of the heart, SA node. And a healthy person says, hey, well, you're between 60 and 100 beats a minute, squeeze. Except I'm going to get sick in the AV node, etc., etc. We know how a heartbeat works, but what does a heartbeat look like? What does a heartbeat look like outside of the body? Not all of us can be as cool as Superman and have X-ray vision. So we have to use the technologies available to us. And one of the ways that we, as lowly little human beings, can look at a heartbeat is by using an electrocardiogram or an ECG. And again, recurring pattern here. Some really fancy science guy came up with this big old word. Didn't like saying it and writing it down. ECG. Cool. There are a few parts to a heartbeat as it appears on an ECG. And you've probably seen this somewhere before. And again, I am not an artist. But some of my work friends would laugh at this little picture here, and I don't care. Okay, this right here is more or less what a heartbeat would look like on an ECG. There are a couple of different pictures or camera angles to an ECG. You'll find out more about that in a 12-lead course or a different other course. Again, nitty-gritty meat and taters here, folks. So this is a heartbeat. more or less. And you know it's going to kill me too. I got to redo this. There. Very good. That's a little bit more workable, isn't it? Alright, so the parts of this, you can see lines and squiggles and moves and curves and everything, and we're getting ready to label every single one of them. Like in most parts of this part of the earth, we read things from left to right. It's no different on an ECG. Okay, there are a couple of parts. We have a P wave, P. We have a Q wave, an R wave, an S wave, and a T wave. P, Q, R, S, T. Pretty straightforward, okay? The P wave here is where we're going to start. So again, we got P, Q, R, S, T. We're going to start here at the P wave. This is the first little bit we notice, and this round little fella here represents atrial depolarization. Now, Corey, this is supposed to be an introductory course. Yeah, I know. Give me a second. You're getting ahead of me. Atrial depolarization. Now, that is a big old word. Okay? Again, science of big words, right? Depolarize is a fancy science word for squeeze. Depolarization is a fancy word for squeeze or contract. Okay? So, assuming we're dealing with an otherwise healthy individual, when a P wave is present, let's see if we can do a quick little diagram here of the electrical conduction of the heart. All right, what's this one? Assuming we're starting at the top. What's this one? Very good. This is the SA node. And that moves down, talks to the other part. Let's shorten it up a little bit here. This comes just underneath the SA node. Very good. You guys are rock stars. The AV node. Coming just off of the AV node. Thick little thing. Splits into two. This is the what? The bundle of his. Very good. I'm not really sure why I'm going from caps to lowercase and everything, but let's roll him here. Bundle of his. Coming off of the bundle of his are the what? We've got a keyword just above these. Right here. Bundle branches. Yes. So this is the left bundle branch. Okay, that makes this the right bundle branch. And these kind of go and they snake back up into the what? Yes, Purkinje fibers. Oh, I'm gonna have to look at my laptop and see that these are still seeable. Time out, class. Sweet, doing good. All right, so atrial depolarization, depolarize, fancy science word for squeeze. Okay, when we see a P wave, we know that the atria are depolarizing or squeezing, which means what part of this system is working. What part of this system, and we've got Bachman's bundle that comes off this a little bit, what part of the electrical pathway is firing or shooting lightning out, generating an impulse? The SA node. Awesome. looking at an ECG or looking at what we can see of a heartbeat, and P wave or atrial depolarization means the SA node is doing its job. We can trace the lightning, that electrical impulse, right here on an ECG. That's cool. Humans, we can like trace lightning. God, it's awesome. P wave means that the SA node here is doing its job. That's awesome. Rock and freaking roll, people. So after the P wave comes this wonky looking doodad here, like we've already talked about, QRS. This middle part is called the QRS complex. The QRX complex. You may have seen these on marketing platforms for various healthcare entities, maybe on the side of an ambulance, or some ill-fated tattoo found on a coworker who once thought it was cool and is now kicking himself because he got a tattoo before he realized what it meant. Anyway, the QRS complex is comprised of up to 3 parts. Q, R, S. Each of these is significant in its own way. Again, take a 12-week course, a specific ECG course to understand that more. What all 3 of these represent is essentially the same, though. All of these represent, where was that color I was using? The entire QRS complex here represents ventricular, ventricular. That's the Latin version. Ventricular depolarization. These scientists, I'm telling you. Okay. Ventricular depolarization. The QRS complex means that the ventricles are depolarizing or squeezing. Okay. Then depolarize means squeeze. Okay. When you see these 2 or 3 lines, sometimes there's 2, sometimes there's 3. 12-week course will tell you more about that. But after the P wave comes the QRS complex, and that means the ventricles are squeezing. It's indicative of ventricular squeezing. Okay, so let's revisit our conduction pathway down here. What part of the electrical cardiac anatomy, or the cardiac conduction system, ensures that the ventricles are squeezing? Yes, the bundle branches and the Purkinje fibers. Each branch here talking to each side of the heart. The left bundle talks to the left ventricle. The right bundle talks to the right ventricle. And we know that that's happening, or we can help figure out that that's happening by identifying our QRS complex, which represents ventricular depolarization. You guys are awesome. You're doing great. I got one little bit left here, though. This little sand dune looking thingamajig. This here is called the T wave. All right, we've already identified that. And it represents something a little bit different. Ventricular repolarization. Ventricular repolarization. What that means is this is when the ventricles are relaxing, they're resting. The squeeze happens right here in the QRS. Ventricular depolarization happens here. Squeeze, all right? But when they relax and they let loose, we can see that right here in ventricular repolarization. Because it squeezes. All right, great, cool. But imagine if the heart that we had drawn earlier had squeezed, okay, and it never let loose. Well, then blood can't go in it, and blood certainly can't come out of it. It has to let go, right? The let go is repolarization. There's a lot more chemistry behind that. Excuse me, a proper anatomy and physiology course will go over that. But we've got squeeze and release. Okay, it's awesome. So you may find yourself wondering, well, how come we can't see when the atria relax? And I've wondered that myself too, as I drop a marker here. we can see when the whole ventricular squeeze and release happens? Excellent question, and the honest answer is that atrial repolarization, when the atria let go, is buried behind the QRS complex. Okay, we just can't see it. The power in the electrical output of the lightning that it takes to get the bad boys, these huge muscly ventricles to squeeze, that's so powerful that it gets overridden. It overrides the atrial repolarization on an electrocardiogram, and we just can't see it. It happens. We know it has to happen, but it happens behind this, and we can't see it. I wish there was a better answer for it, but that's what a cardiologist told me. Oh, it happens. You just can't see it. Gotcha. So that's it. There we have it. We know where blood comes from. We know where it goes. We know how it gets there. We have the atria, the ventricles, all 4 valves, all 5 major blood vessels. We know that the blood flowing through all of these occurs because of lightning, an electrical impulse generated by the SA node in an otherwise healthy individual. That impulse travels down the heart and a little bit back upwards and can be traced the whole time on an electrocardiogram. The skills video accompanying this lecture will be posted also, where we'll go over how to obtain an electrocardiogram. We'll also review everything here again. Thank you for your time, and should you have any questions, my contact information can be found on the course syllabus. Thank you.